Assalamu alaikum. This is Mustafa Nabil Ali Askar, and today I'm going to present you my paper, The Development of Prediction Models to Detect the Presence of MGMT Promoter Methylation for Prognosis of Brain Tumor, supervised by Dr. Asian. So, brain tumor is the 10th leading cause of death worldwide. According to a study of brain tumor in neurosurgical department in Telangana in 2018, around 12.4% of the cases are below 20 years old, 28.2% are between the age of 20 and 50 years old, and more than a half with 57.8% of the cases are above 50 years old. Around 43% of these cases are males and 56.3 are females. So brain tumor can be diagnosed using invasive methods and non-invasive methods. Non-invasive methods such as scans from MRI, from CT scans, and PET. Invasive methods are surgery. So in our study, we will focus on MRI scans. MRI has four sequences: T1W, FLAIR, T2W, and T1WCE. T1W and T1WCE has short TR and TE, while FLAIR and T2W has long TR and TE. The CSF is dark in T1W, FLAIR, and T1WCE, while it's bright in T2W. The fat is light in T2W, FLAIR, and bright in T1W, and gray in T1WCE. So these scans can detect brain tumor, and brain tumor has MGMT promoter methylation, which help us with the brain tumor treatment. So MGMT is a DNA repair enzyme that may repair the damage induced by alkylating chemicals such as DMZ. MGMT is accepted as a biomarker in glioblastoma. MGMT promoter is either methylated or unmethylated. Methylated MGMT decreases repairability of damaged cells, so the TMZ alkylating treatment will be effective. People who has unmethylated MGMT will TMZ will be less effective to them because cells are able to fix the damage produced by TMZ. So in our case, we have two problems: surgery and time. Surgery, which is the only widely accepted approach to identifying GMT promoter methylation status, which involves invasive techniques and might lead to serious consequences. While it can take several weeks to determine the genetic characterization of the tumor. So this is the scope of our work. So firstly, dataset will be obtained from rats. Then we will explore and visualize the data for better understanding. Then the images will undergo some pre-processing techniques to clean them. Then we're going to determine suitable deep learning algorithms for MGMT prediction. Then we're going to build a graphical user interface to make an interaction between the system and the user. Three research gaps were found in this study. First, is the list references on GMT methylation detection via MRI. Secondly, the lack of studies regarding analyzing sequences of MRI and comparing them and see which one is more effective to MGMT promoter methylation, detection of MGMT promoter methylation. Thirdly is the absence of user-friendly interface. So let me explain the flow of our study. So firstly, we obtain the data, then we apply EDA and data visualization for better understanding. Then these images will undergo image pre-processing techniques to clean them. Then we're going to train our models and evaluate them. On our case, ResNet50 and EfficientNet V2. Then if we are satisfied with the results, we're going to choose the better model for our GUI design. If we're not satisfied, we're going to uh, apply another image processing techniques. So our data consists of training sets and test sets. Our training sets has 582 samples. Inside each samples, there are four subfolders correspond to the four sequences of MRI. The same way with testing sets, however, there are 87 samples. The training set has also a CSV file for the labels of the images, either methylated or unmethylated. So EDA and data visualization are crucial for our understanding to the dataset. They uncover hidden insights and relationships, guiding further analysis and decision making. Train and tests will be discussed in this session. So 47.5% of our datasets are having unmethylated MGMT promoter, while 52.5% are having methylated MGMT promoter. Flare has the least number of files and with an average of 127 files per case, while T2W has the most number of files with around 100,000 with 171 file per case as an average. In the test set, the flare also has the least amount of numbers of files, with around 11,000 images, with an average of 124 files per case, while T1W has the most number of files here, which is 26.276 thousand files, with an average of 137 files per case. So the image preprocessing techniques that have been applied on our datasets are the black images removal, which will allow the model to focus on key pattern and features, the value of interest lookup table application to increase the contrast or visibility of regions, also the image normalization to scales the pixels values to fit within range 0 to 1, image type conversion from integer 16 to integer 8, which results in small file size while having the same image geometry, which preserves crucial spatial information. So these are the results of our preprocessed images. As you can see, there is no differences. However, the size has been decreased. So we ended up having 200,000 images in the training set while having 50,000 images in the validation set and having 65,000 images in the testing set. So let's compare the two algorithms that we are going to evaluate in our study, ResNet50 and EfficientNet-V2. So the architecture of, well, both of them are CNN architectures, while ResNet50 has 50 layers and EfficientNet-V2 can be up to 182 layers. The parameters is 24 million for ResNet50 and 4 million for EfficientNet-V2. Both has been added global average pooling and dropout and dense on their layers, while having the loss function used as the binary cross entropy, while the loss function was the binary cross entropy. Each slice of images were treated as an individual images. So, in to evaluate the performance of our models, we are using four metrics: accuracy, precision, recall, and equality. So we use the micro average, which aggregates the scores across all classes and takes their average. As you can see, T2W outperformed other sequences and achieved around 95% for ResNet 50. It has the highest recall and F1 score with 0.95. That means that T2W images fluiding provides essential information concerning fluid accumulation, edema and lesion, and MGMT promoter methylation, which is effective utilization of unique traits and patterns. Let's now analyze our T2W ResNet 15 model. As you can see, both training and validation metrics improved gradually over the first 10 epochs. Training loss has fallen from 0.8 to 0.1, while likewise the validation loss from 0.6 to 0.2. Moving on the last 10 epochs, the model performance improves even further. The training loss is reduced to 0.0071 while the accuracy increased to 0.9975. The validation loss is constantly low, ranging from 0.22 to 0.29, while validation accuracy is high, reaching 0.95. So, Brat's data sets did not release its result of the testing set, limiting comparing and measuring the accuracy of our prediction results with the actual results. As a result, a validation set has been utilized to analyze and evaluate the performance of estimations as discussed earlier. So this is the graphical user interface that has been developed to make an interaction between the system and the user. Here, here the user can upload the decom file, which will convert it then to the integer 8 to process, will apply image processing techniques. Then the model will predict if it's either MGMT promoter or if it's methylated or unmethylated. Then the status will be displayed here, and also the TMZ effectiveness, either it's effective or not, will be displayed here. So the study successfully achieved all set of objectives: data visualization and EDA techniques, and the utilization of deep learning algorithms with different MRI sequences to predict the MGMT status. Also developing a user interface for MGMT promoter status identification. And thank you.